The Actor Model with Akka.net and Aaron Stannard, Part 1.
The Azure DevOps Podcast is a show for developers and DevOps professionals shipping software using Microsoft technologies. Each show brings you hard-hitting interviews with industry experts, innovating better methods, and sharing success stories. Listen on to learn how to increase quality, ship quickly, and operate well. And now your host, Jeffrey Palermo.
Welcome to the show. I'm Jeffrey Palermo, your host for helping you and your teams move fast, deliver quality, and to run your software with confidence in Azure, all while using everything the .NET ecosystem has to offer. The podcast is sponsored by ClearMeasure, a software architecture company that empowers .NET teams to be self-sufficient and able to deliver world-class results, and they are hiring. So go to clearmeasure.com/careers for architects and also for .NET engineers who would like a path to become an architect. And finally, be sure to check out the new video show, Architect Tips. Now, this interview was amazing, and there is so much that we're splitting it into part 1 and a part 2. So this is part 1. So check out episode 173 for part 2. Our guest on the show today is Aaron Stannard, and he's the founder of Petabridge and Sdkbin, building open source tools for .NET developers to build concurrent and distributed applications. He also founded MarkedUp Analytics, a real-time in-app marketing and analytics service used by over 1,000 developers. And he's also spent some time inside Microsoft as a Startup Developer Evangelist. Aaron, welcome to the show. How are you, sir?
Thanks for having me. I'm doing great. Had to step away from my open source duties yesterday to cut down a Christmas tree, since this is my only available time to do it between now and the actual holiday. But feels good to actually get some natural sunlight versus the fluorescent ones in the office.
Nice. So you harvested your own tree.
Yeah, it's a thing we've done. So I live in just about an hour north of Houston. And there's a little farm that specializes in doing Christmas trees, and they make a whole good deal out of it. I'm also a new father. We have a 4-month-old now. Thank you. And so this is our first time. So we cut down a tree last year, right not long after my wife and I found out that we were pregnant. And then this year we brought the 4-month-old with us, a little baby girl, and she was delighted seeing all the big trees out there and a bunch of goats and chickens they had on the farm. She thought it was amazing. So awesome. Next year when we bring her back out there, she'll be big enough to actually maybe start running around some of the little groves there. So that's always a lot of fun doing it. And cutting down a Christmas tree is not as hard as you would think, actually. You do need 2 people to do it, though.
Yeah.
But yeah. Yep.
Nice. Yeah, I think we've done that one time, found a Christmas tree farm, but then the rest of it is, all right, where's the Christmas tree tent or Home Depot or whoever's selling them? So.
Yep, I get it.
Awesome. Well, just by way of introduction, there's tons of people who I'm sure saw your presentation at .NET Conf or have followed Akka.net, but there's so many developers out there, and there's there's a group of listeners who've never even heard of Akka, but more importantly, they haven't heard you speak. And so, give it a little about your background and maybe some key moments that led up to what you're doing now.
Yeah, absolutely. So I'll go ahead and start with you mentioned from my bio there, a company called MarkedUp Analytics. So I've always been so my dad's a software entrepreneur himself. He was originally so he immigrated to the United States from England to get his PhD in theoretical chemistry at UCLA. So his PhD doctoral thesis was on early MRI technology, that type of stuff. This is in the 1970s. He got exposed to computer programming while doing that PhD. Went on to, he basically figured out, my dad's a smart guy, he figured out that the fastest route for him to get naturalized in the United States was to work for a government contractor. So I worked for a contractor back down in San Diego, California, where I'm from originally, and actually did some contract work for NASA. Wrote some software to help figure out what the best coding was to go ahead and resist the buildup of static electricity on the space shuttle, since the space shuttle would have one half facing the sun, the other half facing the earth, and you could end up building an ionized charge on the side that's being bombarded by solar radiation. So they had to come up with a way to come up with some program models to go ahead and figure out what the best way to treat the ceramic tile was, so you could basically discharge any of that electricity being built up. Anyway, he started a bunch of software companies in the 1980s and in the 1990s, and he's still got one that he's running today. My career kind of mirrors his to a large extent. I went to college, got a computer science degree. I went to work for him for a couple of years, and then I got a job at Microsoft. While I was there, a couple of the big things that were happening so I joined Microsoft in 2010, right as Windows Phone 7 was getting launched. So that was kind of the first thing I worked on. And my role, sort of appropriately enough at Microsoft, was a Startup Developer Evangelist, working on the BizSpark program back in the day.
Yeah.
Before we had free editions of Visual Studio and Visual Studio Code, the way startups that didn't have a lot of capital would get access to those tools and products was through Microsoft's BizSpark program. So I was their evangelist for Southern California. So I basically was located in like Santa Monica, sort of the west side of Los Angeles. And I also teamed up with my compatriot who was based in Silicon Valley. We worked together quite a bit. But I got exposed to Azure. That was the other but that was probably what I spent most of my time working on. Was Scott Guthrie took over the Azure organization after I'd been there for about maybe a little bit less than a year. So I worked on the Azure program quite a bit. But one of the things that was kind of coming out right as I basically completed my first year at Microsoft was Windows 8 and the launch of the Windows Store. And based on the internal metrics that we were publishing about the adoption numbers and how big the Windows 8 App Store was going to be, I bought into all of what we were saying internally about this being, quote, the greatest software development opportunity ever in terms of the economic opportunity of being able to sell apps directly to Windows users through a built-in store. So I quit Microsoft right after I got my second year bonus in 2012. And I went ahead and founded MarkedUp Analytics. And our first product was basically a real-time analytics system built on top of ASP.NET MVC4. We used RavenDB for a little bit. We switched to Apache Cassandra when we needed to scale because we ended up having 3 or 4 days of like cumulative 600% growth. So we went from doing like 10,000 events a day to about 16 million events per day in like the span of 3 days. And when I say cumulative, meaning like that number of events stayed there and continued to grow, basically. So at our peak, the company eventually, the business failed. I did raise some venture capital for that startup, and the business did fail. But at our peak, after about 2 years, we were doing about 100 million events per day. And at the scale we were growing, we probably could have gotten up to 1 billion events per day within, let's say, another year or so. The real story of Akka.net and what I'm working on now comes from our second product we built at MarkedUp Analytics, which was a real-time marketing automation system. Now, to kind of explain how this works, so we had a very successful, from a technical perspective, real-time analytics product that was built primarily on top of Apache Cassandra's real-time counter system. The way Cassandra models data, I won't get into all the data on it. I won't get all the details, but it's very useful for doing time series, and counters are very useful for doing real-time metrics. So we had all that in place already, and that system was very well designed and efficiently built. And we had all this great analytic data coming in from all of our customers. We wanted to reuse that same analytic data that we already had to send targeted push notifications to users who performed certain goal-oriented tasks inside the application, such as they took a look at in-app purchase but didn't buy. So maybe we could send them a targeted push notification with a discount code and see if we can drive conversion there. One of the keys to making that system convert well, we actually tested and measured this, was the push notification had to arrive within like seconds of them hitting that goal. If it happened 10 seconds later, the effective conversion rate fell by like 40%. And that means that's a very big difference in terms of how well our product works. So we needed to have a real-time application that could personalize these targeted campaigns that were specified by our customers, the app developers themselves. So it had to be totally customizable, had to work in real time, and it had to do it across an arbitrarily large number of tenants who have an arbitrarily large number of users. This is actually a fairly complicated scaling problem. One thing that will absolutely not work at that scale is delegating all of your state to a database. You will get annihilated by the unknown black box performance characteristics of any database system, including something that works in memory like Redis potentially. The only way to make this design work at scale was decentralization. We had to go ahead and make it so each of the application instances that were processing these campaigns had the ability to take advantage of a principle known as state locality, meaning the data that is used to do the work is adjacent in memory to the code that performs it. If you have a combination of, let's say, a soft real-time processing guarantee, which is what we had, meaning like your application must respond to this input within this finite amount of time, or your service gets degraded. And there's a lot of, I'm talking about marketing automation as our use case. There's thousands of business cases that all have that constraint. So there's that constraint. Then the second constraint is you have to be able to do this for an arbitrarily large workload whose boundaries are not determined at design time. They're determined at runtime. This means you have to have the ability to scale horizontally is what you really need in order to do that. So I racked my brain around how do people solve this problem? And the one thing I kind of intrinsically knew was that we would need to incorporate state inside the application. But because, like most software developers, I'm an elder millennial, I'm 36. I sort of got most of my background doing CRUD web applications built on top of a SQL database. I did some of that in PHP, did some in Node, and I was doing it now in .NET, which I had been doing both before and after I worked at Microsoft. But I knew intrinsically we needed some other way of managing state, but I couldn't wrap my head around how to do it. Sure enough, it turns out the answer was we needed to go ahead and have a way of essentially allocating these sort of arbitrary objects that could live between multiple successive HTTP requests in memory. And actors turned out to be the best concept for implementing that. The actor model is the sort of overarching school of thought on how you go ahead and break apart an application to lots of these individually addressable, let's say, cloud objects, for lack of a better word, where each object in our case could represent one user using one application. And then that object could have a bunch of child objects, which might represent each possible campaign this user could be in. And so you can imagine we have a stream of events coming in, 100 million a day, and those 100 million events might be partitioned across 30 million users. And each of those users might be able to qualify for 10 different campaigns. So you can go ahead and imagine, let's say, the combinatorial complexity there, where it's 100 million events getting partitioned across 30 million users with up to, let's say, 10 campaigns each, right?
Many thanks to our podcast sponsor, ClearMeasure. ClearMeasure is a software architecture company that empowers clients' development teams to be self-sufficient, moving fast, delivering quality, and running their systems with confidence. Whether starting a new project or developing new technologies or techniques, ClearMeasure sets up your team to deliver world-class results. Learn more at www.clearmeasure.com. ClearMeasure, empowering software delivery.
That's a lot of complexity. The way you go ahead and wrangle that is using a tool like the actor model, which has a hierarchical approach to how objects are organized. It looks like a family tree. So you have, let's say, an aggregate root. If you're using a little bit of domain-driven design terminology here, you have an aggregate root that represents an actor in one instance of your Akka.NET process that kind of represents all possible users inside your system. And every time an event comes in, that actor is going to check, okay, do I have a child that corresponds to this user ID, where this user ID is a property on that event that you defined yourself as the C# programmer? If I don't have an actor that corresponds to that user ID, I can go ahead and dynamically instantiate one. And that's very inexpensive to do. And that actor will be programmed that when it starts up, it's going to go ahead and fetch its previous state from a database, and it's going to rehydrate all of its state into memory. And that memory is going to be what it uses for processing its instructions and its rules. So the first thing that our little user actors would need to do, this is all theoretical, by the way, at this point. Akka.NET does not exist at this point in the design formula.
Gotcha.
But the actor would basically would get hydrated into memory. It would load up some key data about this user, such as what application they correspond to. And then we'd go ahead and load, does this from another area, another set of actors in a separate hierarchy that are all part of the same process would say, okay, get me any of the campaign definitions for this user. And those would already be cached in memory. So that would avoid another database lookup, which matters when you're dealing with latency here. We'd go ahead and cache those, and then we'd create little state machine actors for that for each one of those campaigns underneath that user. And we would be able to process the sort of rules in memory very quickly for that. And every time a user's state would change as a result of an event being processed for that campaign, we would go and persist that asynchronously. And that was sort of the model we came up with. And we said, okay, great. This is fantastic. The actor model is 40 years old. It was originally, the original actor model white paper came 2 years after the original relational database white paper did. So this would be like 1973. I'm right, or maybe 74. I can't quite remember off the top of my head, but I'd say, okay, this is fantastic. It's the year 2014. No, this was late 2013. Sorry, I'm getting old here. So late 2013, I'm like, okay, so the actor model's been around for 40 years. .NET is a mature platform. Surely there's an actor model implementation somewhere that we can use. And the answer is, of course, no, there wasn't. And this is because at the time, the .NET open source ecosystem around 2013-14 was utterly terrible. You couldn't even get a socket server implementation like at that point in time. So we decided that the lesser of two evils, we only had a small team. We had a team of about 3 developers. One approach would have been to try to port basically Akka, which was a very popular actor model implementation in the Java ecosystem, port that to .NET, try to use it. Or the other approach would have been to try to port our application to the JVM and use that. We ultimately decided to go the former approach and port Akka to .NET. And within about 5 months, we're able to get that. We're actually able to deliver that product, get it to market. That business failed for reasons that have nothing to do with Akka.NET. It's just no one made any money on the Windows Store. So about a year after our first development efforts began in Akka.NET, we closed down shop. But by then we had a thriving open source project and a community of users who were starting to use it for their own applications. And after I put out my, we're shutting down our business blog post on the MarkedUp blog, I started getting offers on LinkedIn to go ahead and do consulting projects for other people's Akka.NET implementations. And so about 6 weeks after our previous business, shut down, I started Petabridge, and we've been in business it'll be 7 years in January, helping businesses build their own Akka.NET applications. And we have customers in just about every industry using Akka.NET for everything from sports betting to massively multiplayer online RPGs to lots of IoT stuff in dozens of different industries to I've even debugged Akka.NET being used in like flight planning systems, all sorts of stuff like that.
Nice.
So it kind of runs the gamut. And that's sort of where Akka.NET came from. So that was probably more context than users even needed. But I kind of like to provide the full Monty whenever I can.
Oh, that's good. That's good. If people were to read that original paper, and we'll include a link to that original actor model white paper in the show notes. But if someone said, you know what, it's just a pattern after all, or it's just a model, why don't I just kind of implement it for myself? How many lines of code was the first rev of Akka that you had to just to get the basics working? Order of magnitude.
So the actor model has a few components to it that make it expensive to build from scratch. So the first is like every object is its own like isolated process, essentially. Okay. And the only way for those processes to communicate is through passing messages to each other. So the reason why you have this process isolation is so what the actor model eliminates is the need for you to have locks and semaphores and other types of traditional memory synchronization mechanisms. The mailbox, which is sort of the queue that the actor uses for processing its messages, is the only place where synchronization really needs to occur in that system. Otherwise, everything's all asynchronous messaging with immutable objects being passed as messages or events, if you will. That part alone, basically trying to design the isolation system, the scheduling system, and also what's called the actor reference, which is sort of the pointer you get to an actor. And on top of that, actors have a very good fault isolation model where if one actor crashes, it can be supervised by its parent and restarted. That alone was probably at least 20,000 lines of code, the bulk of which was testing probably. Then you get into the much more complicated stuff, which is if you want to distribute actors across multiple processes and build a cluster or a network of actors, that requires a fairly sophisticated serialization system for being able to transparently address messages back and forth between actors and different processes. It requires a robust addressing system. It also requires a reliable network transport, we're on our third official transport implementation now. We're about to move on to a fourth and a fifth in order to try to improve performance. And there's also all sorts of other fun problems our current design can run into, such as basically anytime you're using, let's say, a single connection to communicate between nodes, you have what's called a head of line blocking issue, which is what happens when someone tries to ram an extremely large message between nodes. Let's say we've got customers sending super high resolution images taken from things like license plate readers. And they're trying to send those messages are, several gigabytes each. Oh, wow. And they're trying to send that over a TCP connection. It's like, man, the fact that it's like what people don't understand is like, well, each one of those TCP sockets only might have 512K of buffer space allocated to do that. So it's like just paging from the user land to system land alone to read from that socket is actually a fairly expensive operation. And they're like, well, this works fine over FTP. And it's like, well, what FTP does is it opens 30 or 40 sockets in parallel and does that using multiplexing, which is one of the things our new transport system is going to do as well. But then you have the problem if I have a cluster with 700 or 800 nodes in it, and every single one of them is trying to multiplex and open several large connections to each other, but get this huge explosion in system memory that gets used up. So it's like, these are all dynamic problems that are not trivial when you kind of look at how they affect the bigger ecosystem. So building your own actor model implementation is probably pretty complicated up until probably pretty complicated unless you decide to strip away a lot of what makes an actor an actor. Gotcha. And those isolation guarantees are probably the most important. The isolation guarantees and the location transparency guarantees are what make them valuable to developers. And those are the most expensive parts to build.
Well, we are going to have to pause it here. This interview has so much information packed into it that we are including a part 2 in episode 173. So check out the next episode for that. And until next time, keep shipping.
You've been listening to the Azure DevOps Podcast, a show for developers and DevOps professionals shipping software using Microsoft technologies. Go to www.azuredevops.show for show notes and other episodes. On behalf of your host, Jeffrey Palermo, and our sponsors, thanks for listening, and may God bless you.